my name is Enakshi. I'm a graduate student at UTF Physics Department. Today I'm gonna talk about the use of RF carpet for ion transport in high pressure xenon gas. First, I would like to talk about why we need this. I work for the R&D of the next group, neutrino experiment with a xenon TPC, searching for neutronless double beta decay, a hypothetical process which, if observed, would prove neutrinos to be Majorana fermion, a particle that is its own antiparticle. Here in the first figure, you can see the double beta decay in which two neutrinos in an atomic nucleus are converted into two electrons, two protons, and two antineutrinos. On the other hand, in neutrinoless double beta decay, the emitted antineutrino will behave as neutrino and they will annihilate among themselves, and as a result, no neutrinos are emitted. And it would mean the first ever signal of the violation of total lepton number conservation, which is an important step towards explaining matter-antimatter asymmetry of the universe. The primary challenges involved is its half-life. Till date, the leading limit is 1.07 times 10 to the 26 years. The next collaboration is searching for this decay using gaseous 136 xenon, a xenon isotope which undergoes double beta decay and creates barium 2 plus ions. Our experiment focuses on identifying this daughter barium ion through an approach called barium tagging. Using single molecule fluorescence imaging, in this process, we use some custom made molecules which when comes in contact with the barium 2 plus becomes fluorescent. We have also developed a custom high pressure microscope which is capable of imaging the single fluorescent barium ions in 10 bar of xenon gas. This is the first ever single molecule imaging in pressure environment ever done. Now we need to figure out how to collect and extract the ion in ton scale volume of liquid or high pressure gas and land them on the molecule sensors. We are using RF based methods to do this. RF carpet have been demonstrated to efficiently transport ions over ton to multi-ton scale in liquid or gaseous environment. However, the highest operating pressure investigated to date has been 300 millibars, but we need up to 10 bars. RF carpets for use at high gas pressure would require ultrafine pitch and very precise RF electronics. There can be different possible geometries for RF carpet. As you can see on the figure, the one we are using have sequence of four circular electrodes with 160 micron pitch. We power the RF carpet with a single frequency four-phased RF voltage. This applied RF voltage generates a micromotion of the trapped ions, which is then correlated with the local electric field directions, leading to a net levitating and sweeping force. To achieve this single frequency, same amplitude, four-phased, that is the 0, 90, 180, and 270 RF waves with a peak-to-peak voltage around 100 volts, we use two C power amplifiers and at the end of the two amplifiers, each two center tap transformers. Depending on the turn ratio of the transformers, we can go up to our desired voltage, and as the two secondary ends of the transformer are opposite to each other, it's capable of giving two RF waves of same amplitude, but of opposite phases. And if the amplifier among themselves are 90-degree phase apart, the first transformer will give the 0-180 phase waves, and the second one will give the 90 to 70 ones, which then at last connected to the four electrodes of the RF carpet. To achieve this, first we have made a circuit model in a simulation called LT-SPICE by measuring all the impedance values of the RF carpet and figuring out the other values like the inductance needed for the transformer coils and etc., which we have custom made in our labs. We are finally able to achieve the four-phased RF wave as you can see on the figure. And finally, the next step is to put the RF carpet inside a gas vessel and test the ion transport as we have already achieved the RF electronics. Thank you, and that's it from my side.